Hey guys, welcome to April 27th recitation. Today we're going to be looking at a few problems from homework 12. Our first one here is number 1 from the PDF of the assignment. So we have two equations here in a predator-prey system. P represents the prey and C represents the predators. And we have a parameter negative P in here that represents a value between 0 and 1/2. So the first thing it asks us about, and the first thing you should always think when you're given a system like this, is how can we put this into a matrix form? So they ask, find the eigenvalues of the matrix A associated with this system. So let's see. So A is going to look a lot like this. Basically, we're just going to take the coefficients off of each of these here. You can think of it just like any kind of linear system that you're setting up the matrix for. So I'm going to convert the fractions to decimals. We're going to have 0.5, 1, negative P, and 1.5 here. All right, so there is our matrix. All right, that's A. We want to find the eigenvalues though. So if we're going to do that, then we are going to have to take the determinant of this minus lambda I. So in this case, we have 0.5 minus lambda, we have 1, we have negative P, and here we have 1.5 minus lambda. So it's going to be a little bit of math. We have a P in here, so that's something to watch out for, is that we don't want to get rid of that. We're going to have an answer in terms of P. If you calculate this out, we're going to get lambda squared. We are going to get, so we have a negative 0.5 minus a 1.5. That's going to give us a negative 2 lambda. Then we are going to get the constant 0.5 times 1.5, which is just going to be 0.75. And then we're going to get our P, and that's going to come in as a plus because we're subtracting the off diagonal. So there it is. This is our characteristic equation. We need to find a way to get values for to get the eigenvalues out of this, values for lambda. So if we're going to do that, we should probably look at using the quadratic formula. So lambda is going to be negative b, so that's 2, plus or minus the square root. All right, so 2 squared is 4, and then it's minus 4ac, right? So 4a is just 1. C is a little harder. C is going to be 0.75 plus p. That whole term is going to be our C. And then all this is over 2a, which is just 2 here. All right, so I'm going to do this a little fast. We have a 4 on the inside in both terms. We can take that out. It'll come out as a 2, right, because it's under a square root. And then we'll have a 2 in every term, so that'll cancel. And that will just leave us with 1 plus or minus the square root of, all right, so on the inside, once we get rid of the 4, we're going to be left with a 1 minus 0.75 plus p. If you distribute that negative, we'll have a 1 minus a 0.75, which is just 0.25, and a minus p, so 0.25 minus p. All right, so there you go. That is our pair of eigenvectors. Now, again, this doesn't say a whole lot, right? Because we don't know what P is yet. So we don't know. We know that we could have attractors, repulsors, saddle points, but we'll have to wait and see. However, this would be the answer to A. This does describe to your eigenvectors. So, all right, let's do this for one of these, and then I'll leave you guys with the rest. They're pretty similar in terms of process. P equals 0, right? So if we put P equals 0 in this thing, well, first off, we want to find what the eigenvector is going to be for P equals 0. We're given a whole list: 0, 3/16, 1/4, 1/2. We'll just do this one to start, though. All right, so we have 1 plus or minus. P is 0, remember? So this is just going to be 0.25 or 1/4. Square root of 1/4 is 1/2. And so that leaves us with 1 plus or minus 1/2. And that would be 0.5 and 1.5 for your two eigenvectors. All right. Now, how does the system what does this mean for the system? What would the long-term behavior look like? All that. So again, we have one of these that's less than 1 in magnitude, one of these that's greater than 1 in magnitude. And when you have that breakdown, you know that you're going to have an origin that is a saddle point. So I'm going to write saddle point here. And I would maybe write a little more, just describe, how you know it's a saddle point. All right, and we also need to figure out information about the attractors and repulsors, just as we did in the textbook. So go away. There we go. Okay, so we have a saddle point. Let us look at the eigenvectors now, because we know that the eigenvectors are going to determine the greatest directions of attraction and repulsion. So first, let's look at the smaller one, the 0.5. Okay. So what this is going to look like is, well, it's a minus lambda I, right? So 0.5 minus 0.5 is just 0. The 1. P is 0 still, so we have a 0. And we have a 1.5, so that is going to become just 1. Augment that with zeros. And this should be a pretty easy thing to reduce. We're just going to end up with a 1 up here. And all zeros in the bottom. All right. So what does this actually mean? This is this might be a little bit of a tricky one to actually convert. But we have one pivot. We have a 1. If we want to write the solution in any kind of a form, it's going to look something like this, where we don't have any information on x1, so we know it's a free variable. So x1 is free. So this parameterized thing here is definitely going to look like that. But x2 is actually a basic variable. It's defined, and it's defined as x2 equals 0. So actually, all we need for this is just that x1 term. That is it. x2 is 0. So we can just write the 0 there, and this is our solution, which means our eigenvector is 1, 0. So let me go to text here. You could say that the greatest, this is the smaller eigenvector, right? So the greatest attractive direction is the line through 0, 0, the origin, and 1, 0, which is the eigenvector we just found. And you could even write like v1, v1 equals 1, 0. Right, so that just says that if you take the eigenvector, the 1, 0 here, and you draw a line that goes through the origin to that is going to be your greatest attractive direction. We can also find the greatest repulsive direction. 1.5 is going to be our eigenvalue for that one, the bigger magnitude one. And let me just oh, I see. All right. Sorry, I'm just trying to pan this up. Okay. So we want to find our greatest repulsive one. So we are just going to want to set this up again, except 1.5 is now going to be our lambda. So that means this is going to be -1. These two stay the same. And this one's going to be 0 this time. All right. Reducing this is not much of a process. You really just multiply this top row by -1. And there we have it. All zeros in the bottom. And we're good. So when we write the solution to this, it's going to look like x equals 1, 1, x2. So maybe you can call this eigenvector v2 here. And then write a little something about how this shows you what the greatest repulsive force is. So our greatest repulsive direction is the line through 0, 0, and 1, 1. All right, there you have it. We can call this V2. Right, so there you go. That is one part of part C. It's looking at the saddle point and seeing which one is the greatest attractive and which one is the greatest repulsive direction. Now I will say you're pretty much a lock for, well, let me look at the P's. Okay, that one's actually going to be a little bit interesting. So for a lot of these P's, notice that we have a 1 plus or minus, right? So that means you're going to have one of these that's bigger than 1 and one of these that's smaller than 1. So that creates a saddle point, right? We know that. But there's an interesting case, and that will be your P equals 1/4 case, where you have 0.25 minus 0.25. That then gives you two eigenvalues with value of 1. So that is something that you should look at, think about. I believe there's a question on the Piazza as well about what happens when the eigenvalue is 1. But I will say you have seen it before, and you've seen it relatively recently in this course. So definitely write up something about that. All right, let me get the next problem here. All right, so this is 6.1, number 2. This is again from the PDF. So we have a list of vectors here, 4-dimensional vectors, and we're asked which pairs from here are orthogonal, and do any 3 form an orthogonal set. All right, so this is a matter of doing the dot product and checking if they're equal to 0. So I'm going to give these labels A, B, C, D. And let's try a couple and just see what we can deduce. All right, so let's do A dot B. All right, so this is you take each of the terms, you multiply them, and then you add. So we have -3 times 1, that's -3. We have 7 times -8, that's -56. We have 4 times 15, that's +60. And we have 0 times -7, which is just 0. All right. If you go through and do the calculations for this, 60 minus 56 is just 4. -3 is going to be 1. So we are left with a 1. And since this is not 0, which is what we're looking for zeros, then A and B are not orthogonal. So these are not orthogonal. Okay, let's look at the other two, I guess. Remember, you have to look at all pairs, so there should be, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, I think you're gonna have 10 pairs you're gonna want to check. So we're just gonna look at 2 here. I mean, the principle's pretty basic. C and D, right? So we have a 0 times a 1, that's a 0. A -1 times a 1, that's -1. -1 times 0 is 0. And -1 times -1 is +1. So we only have 2 terms, and they actually do add to 0, so that's good. So we know that C and D form an orthogonal pair. Now, the interesting thing here is it doesn't just want all the orthogonal pairs. It does want that. So find all the orthogonal pairs, but it also wants to know, are there any orthogonal sets of 3 of these? So for you to have an orthogonal set of 3 of these, right, you would need 3 different pairs to all be orthogonal to each other. So if you can find any 3 of these, where if you match any 2 of them to each other, they get 0, then you found an orthogonal set. And orthogonal sets are neat because that gives you something, think about R3, think about the 3D world that we live in. We like to define everything with X, Y, and Z. That arrow is terribly backwards. Right, we like to define everything with X, Y, and Z, which are orthogonal vectors, right? Now this is R4, so, it's a little bit different. But if you can find 3 orthogonal lines, that gives you a basis for R3. Likewise, if all 4 of these were orthogonal to each other, that would be a basis for R4. So anyway, go through that, do all these dot products out. It's mostly just multiplying and adding, and see if you can find any that meet that criteria. All right, next up, we have one from the textbook. So let me pull it up here. 6.2, number 28. right? So we're looking at more of a proof kind of question. We're supposing y is orthogonal to u and v. And we want to show that y is orthogonal to every w in the span of u and v. All right, so let's write the givens and what we need to show, because I think that'll help us out quite a bit. We know that y is orthogonal to u and v. That is basically the same thing as saying that y dot u equals 0 and y dot v equals 0. All right, these are both given to us. Now we want to be able to show, so I'm going to draw this double line here with a question mark over it. We don't know how to show it yet, but we know that we should be able to show it, that y is orthogonal to some arbitrary thing in the span of u and v. So if you remember span, that's the linear combination one. So it's just going to be some constant times u plus some constant times v, and showing that this is 0. Right. Well, can we do this? You might be reminded of properties of like linear transformations here, or I guess like linear operators. And we're kind of going down that path, right? We have a dot product, and we're basically interested in knowing, does this sort of distribute through? And it happens that it does. We have properties of dot products that tell us we can actually distribute them. So I think the best way to show this would be to kind of start here actually and work your way back to the basic properties. Right? So if you were to distribute this through, we could get C1 y times u plus C2 y times v, and you could maybe write a little something about how this uses the rules that are defined in the book, and this equals 0. All right, so how do we know that this equals 0? Well, y times u is 0, that's given to us, so we have a C1 times 0. Over here, y times v is equal to 0, so y C2 times 0 equals 0, and there you go. 0 equals 0. So this is a little check mark. So there we go. Y is orthogonal to any arbitrary vector in the span of u and v. All right, the last one is also out of the book here. It is another sort of proof style question. And this one uses an interesting theorem that's given to us in the book. Suppose W is a subspace of Rn spanned by n non-zero orthogonal vectors. Why does W equal Rn? All right, so this is kind of an interesting question. Let's work this out in R2 first, just for the sake of example. All right, so W now, if we're using this R2 example, is a subspace of R2. Right? And it's spanned by 2 orthogonal vectors. All right, so W is spanned by 2 orthogonal vectors. Let's plot them out, I think would be the best way to do this. All right, so they could look like anything, but let's just imagine, I don't know, maybe they look like that. There's this green thing here, and we need something orthogonal, so it's got to be exactly 90 degrees off. So it'll be there. And we have this, we know that there is a 90-degree angle there. All right, and we're interested in finding out, does this span, well, you know, we know that this span of these perpendicular vectors represents W, and we're trying to show that W equals R2. So the span of these two vectors equals R2. And that makes sense, doesn't it? You've seen change of coordinates before. You've seen non-standard coordinate bases. You know that generally if you're looking at different coordinate systems, if you have perpendicular bases, that those are necessarily going to be linearly independent. And that's actually a theorem that we've been given. But just if you were to think about it, right, you could actually draw out. So let me draw this out to show you. You could draw out a little grid here that you could basically, just try making these lines straighter. You could draw a little grid here that would allow you to get to any point in R2. It's not going to be like standard coordinates, right? It's going to be a little bit different. But if you wanted to get, say, up here, you could just follow these green and red lines to get there. And because they're perpendicular, you know that they're guaranteed to be, independent in that way. So this holds up in Rn, and there's a theorem in the book that kind of shows us this. So let's write it out. Let's write out what you would probably want to say for this one. All right, so if W is spanned by n non-zero orthogonal vectors, there is a theorem, I think it's called Theorem 4 in the book, that says orthogonal vectors are linearly independent. And I believe this is called Theorem 4. Right, so this says if we have orthogonal vectors in any dimension, we know that they are going to be independent of each other. All right, so now we have that we are in Rn and we have n linearly independent vectors. That is the definition of a basis. So, it's going to be a little more writing than I'm doing here. You'll have to explain, all right, this uses the theorem to show that because we have orthogonal vectors, they are linearly independent. Because we have n linearly independent vectors in Rn, that means that the vectors form a basis. Would be, I guess, the best way to say this. So the vectors form a basis. And since the vectors form a basis for W, or I'm sorry, since they form a basis of Rn, right? Because it's n linearly independent vectors in Rn. And because W spans this basis for Rn, that means W is Rn. So that's going to take a little bit more explaining too. Why is that true? Think about it. Why would you, if you're spanning the basis for Rn, then why does that make you Rn? And it's basically because, it's the definition of a basis. So, explain this out with a few more words, a little bit more. But this is the general principle. And if you can understand how these ideas connect, you should be okay. All right, so that's all I have for you guys this week. Let me know if there's any issues with this new app. OneNote was giving me a lot of problems this week, so I figured I'd try recording on something new. Yeah, let me know if you have any feedback. Otherwise, have a good rest of your week.